So this is a little quick little tutorial on voltaic cells, and also called galvanic cells because of Luigi Galvani and Alessandro Volta's discussion about whether electricity was in fact from a biological, or created from a biological point of view or from a physical science point of view. And that discussion led Alessandro Volta to create the first battery. Because of those discussions, we have now the voltaic cell or the galvanic cell to talk about, which is an important application of redox because think about this, the device I'm using, the device in your pocket, is all run by batteries, which are voltaic cells, which are splitting the redox reaction in half. So what I'm going over today is something called a Daniell cell. It's one of the first wet cell applications of batteries that we have. And all batteries, although they could look different and have different ways they do things, they all do the same things to create a voltage, a potential difference. And they all have similar types of components. Although they may look different, they may have different ways they go about doing them, the components I'm covering here today are all the same for all batteries. So let's get started. So what I have here is I have a zinc solution, a zinc nitrate solution, and a copper nitrate solution. And I'm going to put those electrodes right in them right away. And I have got a copper electrode with the copper nitrate solution here. So if you can see the blue color in the bottom here. And I've got this zinc electrode in the zinc nitrate. Okay, now what I'm going to do is I am going to connect the leads in a second to see if we can create a voltage. I have a voltmeter right there. But before I do so, I need to look at this voltaic cell, and I need to be able to distinguish where is the electrons going to be produced and where are they going to be pushed from and where are they going to be pulled from. I like to say push because the side that oxidizes pushes the electrons and the side that reduces kind of pulls them along the circuit to create this energy that pushes current along. So we're separating our half reactions. The first step in any voltaic cell is to figure out who is the anode and who is the cathode. So the first step is I have two metals. I've got my zinc right here, and I've got my copper. So I'm starting with two electrodes, which are going to be the anode and cathode of my battery. Well, okay, so where do I get started? Because I have to know who is going to produce the charge or electrons and who is going to accept them. So what we do is we go to a net potential table to decide who is better at oxidizing, zinc or copper. So let's do that. And when I do that, I get this table here. Or no, I get this table here. Okay, now with this table, you can see my zinc is on top, and my zinc likes to oxidize because its reduction potential is so small. It's minus 0.76, which means that zinc loves to oxidize compared to, let's say, other metals like iron. Okay, aluminum with a smaller reduction potential means it likes to oxidize better. So what I did with the zinc is I made the negative 0.76 positive because it's oxidizing. Now where is copper in relation to the zinc? Well, the zinc is up top, and my copper, is somewhere on the bottom. Let's go see if we can find it, and there it is. So there's my copper, and my copper, is lower than the zinc. So in this table, copper is not as good as oxidizing. In fact, it's so poor at oxidizing, its oxidation potential would be negative 0.34. So the copper plus 2 ions love to reduce. They're positive. So when you think about this, putting positive copper plus 2 connected to the copper electrode, all right, with in junction the zinc oxidizing, we're going to have a collective voltage of 0.76, on top here, plus the 0.34 volts. And that's going to give me a 1.1 collective. And the reason why that works is I got to push and I got to pull. Who's going to push? The zinc is going to push the electrons, through the circuit, and the copper plus 2 is going to pull them. And the collective efforts give me a 1.10 voltage. Let's see if I can get that. So back to where I was, and let's do what we talk about here, the half reactions I have written. So zinc is going to be my anode, so I'm going to write it here, the anode. Now how do I know that? It's better at oxidizing, and there's a nice mnemonic that helps you remember this. It's called anox Okay, don't think you can see that. So we'll try that again. Anox, red cat. And what does that mean? At the anode, we've got oxidation. At the cathode, what do we have? We've got reduction, gaining electrons. So the electrons, okay, are going to basically come from the zinc. The zinc is going to what, party people? It's going to oxidize and produce these two electrons. So the zinc, solid, in a metal at zero solid, let's go, and let's make this in color we can see. Let's go green here. So a piece of zinc is going to become zinc plus 2. And the zinc is going to get smaller. Every time a piece of zinc becomes zinc plus 2, a piece of the zinc, the solid zinc, disappears and transforms itself to aqueous ion. So this electrode is going to get smaller as it pushes the charge. And that charge is going to be pushed from the anode always to the cathode. And that cathode is going to have this charge sort of built up. What I mean by that is we're pushing charge around. So we would say that these electrons come from the, I'm just trying to get my ink here lined up. I would say that the electrons build up on this electrode here. You can see that there. And what happens is the copper plus 2, already in solution, and I'm going to write it right here, jumps on these two electrons, and what happens is that copper plus 2 gains 2 electrons to become pure copper, which is solid at STP. So that means that we're going to have some plating occurring. This side of the electrode is going to get bigger as the half reaction on this side goes forward. And it's the copper plus 2 that specifically is getting reduced, and it's pulling the charge from the zinc this way, from the anode to the cathode. And the collective efforts of the zinc pushing, oxidizing, and the copper plus 2 what? Pulling or reducing, we get a voltage of 1.10 volts at 1 molar concentrations. Okay, moving forward here. So let's see if that occurs. Let's put that together. So I'm going to put my positive lead on the cathode, which is the copper, and I'm going to put the negative lead to the anode, and we, by convention, call the zinc the negative, and which is the anode, we call this the negative electrode. Let's make that into something we can see, the negative electrode, and we call this one the positive electrode. Now why? Well, by convention, electrons like to flow to a positive, and it keeps us also with our small little minds. Now, if you noticed, we have no voltage. What am I missing? Well, for those that know, we're missing something called a salt bridge. So let's draw that in. Salt bridge lets the charge, well, how can I say this? Well, I can say this by, if you look here, we're building up zinc plus 2. Over time, let me write it over this side, zinc plus 2 is building up. So as zinc oxidizes and becomes zinc plus 2 ions are building up. And if that occurs, this beaker is getting positive, and electrons won't leave a positive beaker. Over here, okay, we have copper plus 2 being lost. Why? Because it's jumping onto the electrons that are pushed. We're losing positive charge. So this beaker here is getting, okay, losing its positive, getting negative, and this beaker over here is gaining a positive. So this beaker right here is becoming positive, and this beaker here is getting negative, and that's never going to work. So we need something to maintain electrical neutrality. So a salt bridge is what every battery needs to try to do this. So let me draw this salt bridge. Now the salt bridge I'm going to use is nothing more than a glass tube. That's a U-tube, not a video on the internet. You know it's good for a bad joke. And I've got some ions in here. I'm going to use potassium, let's say nitrate. And what do you think is going to happen, party people, when I put this in? Well, you know it's going to work because you're waiting for me to make it work. But the positive ion is going to migrate into this cell to replace the positives that are lost.